everyone, welcome to the lecture number 25 of this NPTEL lecture series on charging infrastructure. In this particular lecture, we will continue our discussion on three-phase AC-DC converter, and if we recap it, what we have done in previous lectures. So, we have understood the operation of three-phase AC-DC converter. By changing this delta value, sign of delta value, we can allow the power to flow from AC to DC or DC to AC, and by changing the magnitude of delta we can able to control the IS current which is been drawn from the grid. Here again we have to ensure that we are maintaining a constant output voltage or regulate the output voltage at V naught, and while drawing the current from the source, that too at unity power factor. So, that is why we have kept this IS phasor and VS phasor in the same phase. There is no phase angle between them. And we have then derived the expression for the inductance value, which we got nothing but under root m V naught by 2 square minus Vs peak square divided by 2 by Fs Is peak square, and that to come everything comes under the under root terms, and from there we can calculate the inductance value, because these are the some of the given in the specification, some of the things are the designer's choice. And once we calculate the inductance value, we have to ensure that the voltage drop across the inductor for the fundamental component should not be greater than 10% of the Vs peak, because otherwise the most of the voltage will drop across the inductor itself for the against the inductor impedance corresponding to the line frequency of 50 Hz. Then we moved ahead and did the sizing of the switches. We saw what are the RMS current ratings, what are the voltage blocking voltage rating of those switches, and after that we moved to sizing the capacitance. Here again we first follow the same procedure what we did in the case of single phase AC to DC converter, where we have did the power balance between the input average power and the output power, and then after that we come to conclusion that there was at the output of the converter there is the second line harmonic frequency component is there, and that second line harmonic frequency currents will be going through the output capacitor, and which corresponds to the capacitor ripple, and then the capacitor size can be selected in such a manner that the second line harmonic voltage ripple is minimal or within the prescribed or within the permissible limit for, given in the specification. However, when we did that, we did a simple thing, we calculated the input power, we calculated the output power, obviously only considering that we have the fundamental current which is flowing through the converter, and then finally what we come to conclusion that we are only having at the I converter there is no second line harmonic component, it only has the DC component, and that DC component, so capacitor blocks the DC current, so it will directly go into the load. However, this is not the case, because if we see the circuit for the fundamental frequency, how our single phase equivalent circuit looks like, where we have the voltage source, we have the AC voltage source coming at the output of the V converter or at the output of the half bridge configuration, and that lead to some current, the fundamental component of current which will be flowing between the two voltage sources. And however, we know that this V converter what we have written over here will also have along with the fundamental component, we also have the harmonic component, and that harmonic component will be at the side bands of MF. More precisely, it will be I MF plus minus J plus minus J, those were the harmonic numbers. So here when we write here N is nothing but I MF plus minus J, and J is again the odd or even number, this J is corresponding to under root minus 1. So, this is the component of the voltages which will be applied at the output of the half bridge, and then we have the inductor. However, in the AC voltage source we have the pure AC. So, that is when for the harmonic frequency component circuit or single phase equivalent circuit, for the harmonic frequency component what we see is that there is no component of voltage from the grid, because grid is pure AC. So, that is why we have shorted it, and that is when we saw that the current, there will be harmonic current corresponds to that, corresponding to that harmonic voltage, and this will be only limited by the impedance corresponds to the inductor for that harmonic frequency. However, this n is very much higher as compared to the fundamental, because for fundamental n is equal to 1. However, most of the cases for the harmonic component, this n is somewhere greater than 20, the harmonic number is greater than 20 or 25. So that is why automatically this harmonic component of currents are smaller. However, this harmonic component of current is the one which is responsible for the frequency component in this I converter current, and that harmonic component of current in the I converter will be flowing through the capacitor, which will actually lead to the current of this capacitor, and thus we have to calculate the what is the RMS current which will be flowing through a capacitor, because that will determine what will be the capacitor size, I mean what will be the series parallel combination of the capacitor bank. So, in order to derive that particular RMS current which is flowing through the capacitor bank, let us see how we can calculate the current flowing through the capacitor bank. For that we have to calculate what is the I converter, which comprises of some average value which is actually going through this load RL and some AC component which will be going through the capacitor. So, we have to calculate that RMS current. So, let us try to first find out how we can calculate the current flowing through the capacitance, because that will determine our size of the capacitance. So, if you look very carefully, this particular we have here VA, which is nothing but Vs peak sin omega t, VBN which is nothing but Vs peak sin omega t minus 120, and Vcn is nothing but Vs peak sin omega t minus 240. Now, this if we see, so this we can say this is VAN, this is VBN, this is VCN. So, now if we look very carefully in this particular thing, we can divide this entire this one. So, if we see from here to here, from here to here, it is one line cycle given as T, which is nothing but 1 by Fs. Fs is the line frequency here we are talking about. And if we look very carefully, we have in total, if we see, we can divide this thing kind of similar looking modes. We can say this is a first thing. So, this is first, now if you look very carefully between this point and this point, we can say this is the, we can say first mode, or let me write this as operating portion 1, this side to this side, this side to this side we can say 2, this side to this side we can say 3 of mode 3, this side to this side mode 4, this side to this side mode 5, and this to this mode 6. And if we try to write down, this is 0. If we write with respect to omega t or with respect to theta, it is 0 angle. Similarly, we can define other angles like pi by 6, pi by 2, 5 pi by 6, 7 pi by 6, 9 pi by 6, 11 pi by 6 and 2 pi as shown over here. Now, if you look very carefully, if we can able to calculate the current flowing through the capacitor in the first mode, the same thing will be there in the second mode, third operating mode, fourth mode, fifth mode, sixth mode. Let us define that as sectors. So, if we have 6 sectors in one line cycle, then we see that in first sector, we see that one of the phases or one of the voltages are maximum voltage, mid voltage and the minimum voltage, and that changes in every 60-degree cycle or after every 60-degree. So, if we can calculate for one of the sector, let me sector 1, we could be in a position to say that the same thing will repeat after sector 2 and sector 3, sector 4, sector 5, sector 6. So, what we can do is, let us try to understand how we can calculate for the first sector the current which is going through the I converter, I mean, we can, let us try to find out the I converter. Then once we know the I converter, we can calculate its average value and its RMS value. From there we can calculate the I capacitor current. Now let us assume that since we know that we have three phases, ABC phases, and we know that these three phases are 120-degree displaced from each other. So thus we must ensure that this one half bridge is actually modulated with the sine waves which are 120-degree away from each other. So let us define these as the modulating wave for phase A, VMA we can say, this is VMB, this is VMC. Modulating wave for phase A, for phase B, for phase C. And we know that modulating wave of phase A is nothing but VMA is nothing but Vm sin omega t, VMB is nothing but Vm sin omega t minus 120, and VMC equal Vm sin omega t minus 240. And if we see this one, this is again with respect to omega t we can say, and this particular thing will be compared with the very high frequency carrier signal, and that carrier signal we can draw like this as shown over here, which goes from minus Vc to plus Vc, while the modulating wave VMA, VMB, VMC will get compared to generate gate pulses for S1 to S6 switches. So this carrier I have drawn for, I mean, very last time period carriers. For understanding, I have just exaggerated that time period. Now if you look very carefully, this carrier goes between Vc and minus Vc, and this will get compared at every carrier cycle with the modulating wave. So what happens at every carrier cycle, all the three modulating waves are sampled and then they were compared, and if we can say that if the modulating wave is greater than the carrier wave, then the top switch is on in that particular phase, and if my modulating wave is smaller than the carrier, then my bottom switch is on in that particular phase. So now if you look very carefully, it is going between minus Vc to plus Vc. So what one can do is, we can, this is going between plus, let us say plus peak value of the modulating wave to the negative peak value of modulating wave. So we can give a constant shift of Vc, that is when we can ensure that our carrier goes between 0 and 2 Vc, and everything is being pushed to, and I mean we can just add everything together, and that is when everything gets pushed to Vc, constant Vc voltage, and that is when everything will come in the positive direction. That is when we can take one of the instances, and in one of the instances of this mode 1 we will have this VMA, VMB and VMC voltage coming over here. So if you see this one, I have given, I mean this TC whatever I have drawn, this TC or TS whatever I have drawn is very much bigger in time period. However, it is very small. I mean generally it is so small that this sampled modulating wave looks like a pure DC. So when we take in one of the switching cycle or one of the carrier cycle in sector 1, what we will get is, this is operating mode 1, for operating mode 1, operating mode 1, or you can say sector 1 is nothing but TC carrier cycle or switching cycle, both are same, where my TC is nothing but 1 by carrier frequency, and you can say that it is nothing but equal to TS, which is nothing but a switching frequency, you can say 1 by FSW. Now if we see, if we take operating mode 1, it is the top one is the VA phase, middle one is the VC phase, and last one is the VB phase, and we have added a constant voltage of VC such that everything becomes positive value. So this one will become, so our red sampled value of red one will be VMA plus VC, yellow one will be VMC, because we have the C phase coming, plus VC, and this is VMB plus VC. This is what we will get. And if we look very carefully, we have already assumed that if modulating wave is greater than carrier, then top switch is on, else bottom switch is on, and in that case my top switch is off, and top switch is off, and here bottom switch is off. So if we take this condition, so in this particular carrier we see that this is the first sample, second sample, third sample, in which we have added the constant value of the carrier voltage Vc. So what we will get is, we will get at this point my S1 switch, this top switch, in because this is for A phase. So for A phase it is S1 switch. My S1 switch here, it is carrier is greater than the modulating, that's when my bottom switch is on and top switch is off. That's when my top switch S1 is 0. At this point my top switch S1 is 1, which is on. From here to here, the in C phase, which is S5, my S5 will be 0, and at that point my S5 will be 1. And in case of C phase, from here to here my S3 will be 0, and from here to here my S3 will be 1. And whenever my S1 switch is on, so if you see the I converter current which is going out of this bridge, it is nothing but the current whenever my top switch of any of the half bridges is on, that's when there will be current which is contributing to the I converter current. So from T0 to T1 period there is no current through the I converter. From T1 to T2 there is only S1 switch is on, so I converter is nothing but the current which is going through here, which is ISA. From T2 to T3, since your S5 and S1 is on, so ISA and ISC will be flowing through the I converter. However, since this is ISC and ISA current is going, this I converter will be nothing but ISA and ISC, because my both S1 and S5 is on. Then at that point of time, at this point of time, what happens is that S1, S3 and S5 is on, and during that time at this place what is happening is we have ISA plus ISC plus ISB, and since we are assuming that we are having the balanced operation of the circuit, so we can say that this is nothing but equal to 0. Assumption: we assume that balanced three-phase operation is happening. If balanced three-phase operation is happening, that's when we can say that ISA plus ISC or ISB plus ISC is equals to 0. Since we have assumed that we have a balanced three-phase operation, so thus at this point when all the three S1, S3 and S5 all the three are on, my I converter is nothing but equal to ISA plus ISB plus ISC, and that is actually equal to 0. That's why the 0 is been drawn. Similarly, between this point and this point also we have the 0 current flowing. From T4 to T5, what happens is that my S1 and S5 is on, that's when my I converter is nothing but ISA plus ISC, and then between T5 and T6 it is my only S1 is on, so it is nothing but ISA is there, and then finally between T6 and T7, since all the switches are off and bottom are on, so my current, there is no current which is going to the I converter, and that's when I converter is nothing but equal to 0. So now we know that in one carrier cycle or in one switching cycle, the Ts duration, for some of the period the I converter carries the current ISA, for some of the period my I converter carries the current ISA plus SC, and in some other duration the I converter has current nothing but equal to 0. Now this is the case only in the operating mode 1, or you can say that sector 1. In sector 2 there could be some other value. In sector 2 we have A, and then we have we have A, we have this VMB will go up as compared to VMC. So that's when we will see that here instead of here we have ISA, and here we have ISA plus ISB, and here we have ISA and ISB, and here we have ISA only. Then in operating mode 3 or sector 3 it will be different. So in all these sectors the magnitude, I mean the steps will remain be the same. That means for some portion one of the phase current will be there, in some another portion both the phase current will be there, and some portion all the three phase current will be contributing to I converter, which is actually nothing but equal to 0. I mean when all the phases are there. So that's when we know that for calculating the RMS current through the capacitor, we must calculate the I converter RMS first for one carrier cycle or one switching cycle, and then whatever we RMS current we get in one switching cycle, then we have to take the RMS current or the average current over one line cycle. So that's why let us first try to calculate RMS or average current in one switching cycle. So this is my T0 value, this is T1 value, this is T2 value, this is T3, this is T3, this is T2, this is T2, T1, this is T0. Now let us try to find out what will be my these values T0, T1, T2 in terms of my modulating signal, how it looks like. If we see, this is nothing but between T0 to this point is nothing but my Ts by 2, half the cycle. Once we have half the cycle, and then the other half cycle we will have the another half cycle. This is another half cycle, Ts by 2. So if we look very carefully, I converter current, it is symmetrical around this Ts by 2 period. So if we could able to calculate Ts by 2 period, we can just do the multiplied by 2 we can do to calculate the to calculate the RMS or average value for I converter in one Ts period. Now let us first calculate what is the value of T0, T1, T2. Now if we look very carefully, T0 is nothing but the portion of the Ts by 2 whenever the carrier is greater than Vma plus Vc. And if we see T1, T1 is the portion of the Ts by 2 whenever the carrier is between Vma plus Vc and Vmc plus Vc. That means between this point and this point. That is nothing but the T1. So we can say T1 is nothing but out of Ts by 2 period. It is the period, it is the period whenever my Vma plus Vc minus Vmc plus Vc out of 2 Vc, because if we go from 0 to Ts by 2, if we go from this point to 2 Vc point. So we have taken out of this 2 Vc, whenever we are in between these two, we are having the duration T1. So this will corresponds to Ts by 4, we can write Vma minus Vmc by capital Vc. This is my T1 value. Similarly, for T2 value we can say that, so we can say Vmc plus Vc minus Vmb plus Vc, and this will give, let us define this as 1 Ts by 4 Vmc minus Vmb by 2 Vc, and this is, let us define this as equation number 2. And then T3 is nothing but the portion of the Ts by 2 whenever my value goes from Vmb plus Vc and minus 0. So we can say that it is nothing but Ts by 4 plus Vc divided by 2 Vc. This is nothing but 4, this is 2, and that we can write T3 is nothing but Ts by 4 1 plus Vmb by Vc. You can say this is nothing but my duration T3. Now this will give me my T1, T2, T3, and that's when I can also calculate my T0. T0 is nothing but out of this Ts by 2 period I have T1 plus T2 plus T3, and when we put down these expressions, what we have is we have Ts by 4 coming out from 1 to 3, and we have Vma minus Vmc plus Vmc minus Vmb, and this we can just write plus Vc plus we can write down this is Vmb, and this everything we can write down as Vc. And if we look, because this is Vc which is coming over here, and this Vc, if we see Vmc will get cancelled, this will get cancelled, and then we can again take out Ts by 2 outside, that will become 1 minus 2 Vc Vma plus Vc, and this when we write down T0, 1 by 2 comes out is 2 Vc minus Vma minus Vc by 2 Vc 2 Vc, so it is nothing but 0 1, we have Ts by 2, and this when we do that we will get Ts by 4, this becomes Vc 1 minus Vma by Vc. Now this is nothing but my T0, and we know that our Vma is nothing but Vm sin omega t, Vmb is nothing but Vm sin omega t minus 120, Vmc is nothing but Vm sin omega t minus 240, and we also know that Vm by Vc we can write something equal to Vm, we can also write that, which is nothing but the modulation index. So we can write down my T1 value Ts by 4, so Vm sin omega t minus Vm plus 2 pi by 3 divided by Vc, and this will be nothing but Ts by 4 m sin omega t minus m sin omega t plus 2 pi by 3. This is nothing but your T1. Define this as 4 and this as 5. Similarly, we can write down T2 Ts by 4, and it is Vmc. So it is Vm sin omega plus 2 pi by 3 minus Vm sin omega t minus 2 pi by 3, and this is nothing but Vc. So we can write T2 as Ts by 4, it is m sin omega t plus 2 pi by 3 minus m sin omega t minus 2 pi by 3. This we can define this as 6, and we can further simplify T1. We can just open up this sin omega t plus 2 pi by 3, and we will finally get, we can get T1 to be nothing but equal to, if we open up this thing, root 3 by 4 of Ts m sin omega t minus pi by 6. We can see this, we can define it 7. T2 we can define from here we can define T2 to be root 3 by 4, this one, Ts m cos omega t. This we can open this one, sin a plus b, if we open we will get this particular thing. So we will get this one as equation number 8. Now if we look very carefully, my I converter is only non-zero during the T1 period and during T2 period. So even if I could calculate T0 and T3, it is of no meaning for me to actually evaluate the average value of this I converter in one switching cycle or carrier cycle. So let us try to use this particular thing to calculate our I converter average. So now what we have to do is we have to now calculate the I converter current. We have to find the RMS and the average current. So let us try to find the I converter average value over the one switching cycle or carrier cycle, you can say over the TS. So we can say average over TS period. So it is nothing but 1 by TS over the this thing 0 to TS I converter over. So in one this carrier cycle, since in this carrier cycle this ISA is constant, ISA and ISC is constant, and that is their non-zero value between T1 and T2 and between T2 and T3. So this particular thing, and it is also symmetrical around this T by TS by 2. So we can write it is, we can just write T1 to T2, this ISA value which is constant value multiplied by this dt plus T2 to T3, it will be there, and here it is ISA plus ISC dt, and remaining period it will be 0. So this will be nothing but, and remaining period will be 0, and since it is a symmetrical around this, so we can just multiply this by this multiplied by 2. So instead of 2 multiplied by this, we can write this, the factor 2 comes from symmetricity around Ts by 2. And we know that ISA plus ISB plus ISC, because of the balanced three phase operation, is nothing but equal to 0. That's when we can say ISA plus ISC is 1 minus ISB. And in these things, since this ISA, ISC and ISB, the sampled current value in that switching cycle, and we know that our switching cycle TS is very much greater than T. So we can say that this ISA, so that's when we can say ISA, ISC and ISB is constant in TS duration. So in that way we can just take out 2T by TS, ISA comes out, and then we have T2 minus T1 plus ISB, ISC I can just write minus ISB into T3 minus T2. Now this I can write T2 minus T1 is nothing but T1. So ISA T1 minus ISB T2. This is my I converter current average over TS duration. Now let us define this as equation number 9. Similarly, we can also find out I RMS. So I converter RMS TS duration, for this TS duration only. Let us define this as square. If we do that, so just we have to find the mean of squares. So if we try to find the mean of square, it is 1 by TS, and again going from 0 to TS, mean of I converter square into dt. Now in TS duration we will just write 1 by TS 0 to TS ISA square dt between T1 to T2, and it is T2 to T3 ISA plus ISC square dt. and then remaining it will be 0, and since it is symmetrical around Ts by 2, so we can just write 2 multiply by that, and that's when we can obtain I converter square value over Ts duration. Here we have purposefully taken I converter square just to avoid the under root term, is nothing but 2 by Ts, and that 2 by Ts, and this ISA and ISC and ISB are constant, so we can just write ISA square times T1, and this one becomes plus ISA plus ISC square T2, and that it will be Ts ISA square T1 plus ISB square T2. This is nothing but I converter square RMS over Ts duration, and this will define this as, let's say, equation number 10. So we understood the average value of I converter over this Ts duration and RMS current over the Ts duration or Tc duration. So let us now calculate the RMS and I average over one line cycle. So now if we look very carefully in this particular thing, this we have drawn it for sector 1. This we have drawn it for sector 1, or you can say operating mode 1. And if we see our operating mode 1, our operating mode 1 is actually between pi by 6 to pi by 2, and it will repeat, and the same thing will repeat over the line cycle. So we just, if we can able to calculate the average and RMS in this, for this operating mode 1, it will be the same for the entire line cycle. So in that case we can now calculate I converter average is nothing but, we can find out for 60 degree pi by 3 going from pi by 6 to pi by 2, and since here we are trying to find average, whatever I converter average over Ts duration, this we will find out, and since it is in angles, this is d omega dt. So this will become 3 by pi by 6 to pi by 2, and this I converter from 9 we can take, is nothing but 2 by Ts ISA T1 minus ISB T2. This nothing but d omega dt. Now this is from 9, and now let us try to put our T1 and T2 value from equation number 7 and 8, and if we put this one, so I converter average will be 3 by pi, this 2 by Ts we can take it out, pi by 6 to pi by 2, and again in this one, since we are doing it for the line cycle, so our ISA will now become equal to Is peak sin omega t, ISB will be Is peak sin omega t minus 2 pi by 3, and ISC is nothing but Is peak sin omega t minus 4 pi by 3, and this when we wrote down here Is peak sin omega t, and here again assuming UPF operation. So that's when there is no phase angle term coming over here. T1 we know our T1 value is nothing but equal to, if we can draw from here, this root 3 by 4 Ts m sin omega t minus pi by 6, and this is minus pi by 6 to pi by 2. Again here it is ISB, which is Is peak sin omega t minus 2 pi by 3 root 3 by 4 Ts m cos omega t, and this will be, this is d omega dt here, and d omega dt here comes in, and this, when you solve this particular thing, we will get I converter average to be equal to 3 by 4 IS peak M value. So this is the value we will get when we make the I converter average value. Now let us see defined as 11, and similarly we can calculate from 10 our I converter RMS means RMS over the line cycle. We can just calculate by again writing the same thing, 3 by pi going from pi by 6 to pi by 2, just like here pi by 6 to pi by 2 I converter, this is converter RMS over TS square into d omega dt, and since it is the root over that, it will be root of this particular term, and that is when you put these values over here. This is pi by 6 to pi by 2 I converter is nothing but ISA square c square T1 plus ISB square T2, and this is d omega dt, and this T1 and T2 we know, T1 and T2 from 7 and 8. This, when you equate this thing and put it, find out the integration, higher computation softwares you can use this, you will get IS peak under root 3 by pi M 5 by 4. This is the value you will get, the I converter as value, and this, let us define this as 12. And once we know, so if we look very carefully in our circuit, we know our this RMS value which is flowing through this, we know through the RL value it is the average value which will be flowing through the I converter. So we can calculate the IRMS flowing through this by the subtraction of the squares of them. So we can write down my IC RMS is nothing but under root I converter. Again this I converter RMS is over the line cycle square minus my I converter average over the line cycle, because this is nothing but over the line cycle, and this average value is again over the line cycle, and then we can calculate the ICRMS by subtraction of that of the RMS value, which is RMS value of converter I converter, which is coming out of the half bridges, and average and minus of the square of I average, because that's the current which is going into the load. So we can say I converter average is going through the load, which is in this case RL, and the remaining will be going through the capacitor. So we can get this value from this ICRMS from this expression, and this you can put it from equation number 11 and 12, and from there you can easily calculate the ICRMS. So if we put ICRMS to be nothing but IS peak square, this is root 3 by pi M 5 by 4 minus I converter average. If we see I converter average value is 9 by 16 M square IS peak square. This is the thing we will get, and this, when you solve this particular expression, we will get the ICRMS, where M is nothing but your modulation index, and IS peak you can easily predict from your specification. So you can calculate Is peak to be nothing but equal to your load power divided by 3 times V phase RMS, and this RMS value multiplied by root 2 will be the Is peak. And here we have assumed that lossless converter is lossless. Converter is lossless. There is no loss in the converter. Otherwise, you can also take some efficiency number and you can divide this by an efficiency to calculate the input power, and from there you can easily predict your Is peak. So we can further this one Is peak under root 3 by pi m 5 by 4 minus 9 by 16 m square. Now if you look very carefully, this capacitor RMS current depends on the modulation index m. So we have to say, depending upon the modulation index selected, this capacitor current will be changing. So with this we have understood how we can calculate the RMS current through the capacitor. That is when we can calculate the capacitor bank, because we can assume the series parallel combination of capacitors. However, still we do not know what will be the capacitance value we can take. So we can calculation of capacitance value. Let us quickly take calculation of capacitance value. So this capacitance value, this value we can define using our normal principle of how much amount of energy you wanted to take it down from the capacitance. So we can define the minimum DC link capacitor. We can say C minimum must be greater than delta P max TD divided by 2 V naught times delta V naught, where we can say where delta P max we can say is the maximum power variation you wanted to variation of the converter. That means whenever we are doing the closed loop operation, what is the maximum power variation you can expect in the converter. That means sudden change in the loads, how much amount of variation, maximum power variation of the converter. TD is, you can say that the response time of your converter, response time of your closed loop, that means how much time it will respond to that change, sudden change. So that's when we can calculate the energy, and that's when we can calculate the energy, and we can say delta V naught is nothing but the permissible voltage ripple, output voltage ripple on capacitor, and V naught is the output voltage. And how, I mean, you will be wondering how we can calculate this. So this particular capacitance you can obtain by just doing the energy equivalence of the capacitance, where the capacitance values goes from V1 voltage to V2 voltage, and this energy which is there has to be greater than, if we wanted to keep it within the delta V variation, is nothing but we can say delta P max TD by 2. And this, when we equate this one, we will get C minimum to be V1 square minus V2 square, it must be greater than delta P max TD, where P max by 2 is the, so when I am talking about delta P max variation, it means that I am talking about the variation of values. So my power delta P max means if this is my PL, this one, so variation goes from, let's say goes from here to here and here to here. So it goes from P1 to P2. So this going from P1 to P2 is nothing but equal to delta P max, and while when it goes to P1, which is away from PL value, or the power which when it goes to more value than the nominal power, so it comes back. So here we get this one value from P1 to PL is nothing but delta P max by 2. So that is why we have written delta P max by 2 here. This will become nothing but V1 plus V2 and V1 minus V2, nothing but delta P max TD. And here whenever this is happening, our capacitor will be having a voltage ripple. Capacitor voltage, if we see, it goes from here to here and here to here, and the maximum value is V1 and minimum value is V2 it goes. So this is nothing but delta V naught. So we can say my V1 plus V2 by 2, we can say that V1 plus the average value of V1 plus V2 is nothing but V naught, and my V1 minus V2 is nothing but delta V naught. So that's when I can write C minimum is nothing but 2 V naught times delta V naught must be greater than delta P max TD, and that will be nothing but C minimum must be greater than delta P max TD by 2 V naught delta V naught. This is what we have written over here. So delta V naught is generally given in the specification, V naught is also given in the specification. This is the designer's choice, and this is again the depending upon the circuit operation, this is the delta P max you will get. So this is again designer's choice or designer's choice. This is the specification given, in the specification it is given. This is again given in the specification, and delta P max is also given in the sometimes given in the specification, or otherwise one can take the required judgment to calculate this value of capacitance. So we have understood how we can calculate the capacitance value, and then once we calculate the capacitance value, how we can design the capacitor bank depending upon the your RMS current of that capacitance, which actually determines how many numbers of parallel branches we needed. And we also know that the voltage rating of capacitor will be, capacitor has to be greater than my V naught plus delta V naught by 2. So this way we can able to actually we can design our capacitor bank. Now in the next lecture we will see the closed loop operation of this converter. Thank you.